It is a pleasure to welcome you to the third edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. The International Workshop on Biogeotechnics was hosted in 2022 during the third edition of the AGERP lecture series. The following lecture on Bioinspired analysis in geotechnical engineering was delivered by Professor Sarat Kumar Das at this workshop. Professor Sarat Kumar Das is a professor and head of the Department of Civil Engineering at the Indian Institute of Technology, Indian School of Mines, Dhanbad, India. Professor Das obtained his bachelor's degree in civil engineering from College of Engineering and Technology, Bhubaneswar, India, followed by his master's and PhD degrees in geotechnical engineering from Indian Institute of Technology, Kanpur, India. Supported by the Endeavour Research Fellowship of the Australian Government, he undertook his postdoctoral training at James Cook University, Townsville, Australia. Professor Das has about 30 years of experience in civil and geotechnical engineering, both in the fronts of academia and industry. His research interests include AI and optimization methods in geotechnical engineering, geoenvironmental engineering, and biogeotechnics. Professor Das has published 100+ technical articles in journals, conferences as book chapters, and has supervised 6 PhD students to completion. He is an editorial board member of Environmental Geotechnics, ICE, and International Journal of Geotechnical Engineering, and reviewed for 60+ technical journals. He is a founding co-convener of the AGERP lecture series, an ex-executive committee member of the Indian Geotechnical Society, and a technical committee member of the International Society for Soil Mechanics and Geotechnical Engineering. Professor Das has delivered many invited and distinct keynotes, including a theme lecture on AI methods in the Asian Regional Conference of ISSMGE.
Good morning, good afternoon, and good evening, everybody. So this bio-inspired geotechnical engineering I started in 2000. I'm a doctoral student in geotechnical engineering, in particular civil engineering in general. I had no idea about this biology, in fact, because because being an engineering student, biology also poor. But that day, there was an inspiring faculty at IIT Kanpur, Kalladmoy Dev. He was giving a course on genetic algorithm. So as a matter of curiosity, I attended that class. So that's how I got interest in this bio-inspired analysis. Then I thought, why we cannot use it in our geotechnical engineering in particular. So this, when I go back, so first I had to thought of where I can apply it, because he was trying to basically teach this genetic algorithm as an optimization problem in analysis. So then I searched in geotechnical engineering where such problem exists, because as a matter of fact, he was giving TORN project. That was a course being taken by different discipline of engineering, computer science, electronics, electrical, and so on. And they were trying to apply in their field, because that time it was a very new tool or technique. So now if we'll go to our stability problem in geotechnical engineering, in bearing capacity problem, if we'll go to research paper, there are lots of research paper in finding out N gamma. Because this N gamma is to be found out by trial and error or through some optimization techniques. And in that bearing capacity problem, what I am finding out? I'm finding out that the maximum load it can take. So we try to find out the N gamma factor, and you will say there are maybe around 50 papers on finding out this N gamma. Next is slope stability problem. In slope stability, we search for different critical surface where it will fail. And since 1967, people are trying to find out this is an optimization problem to find out that factor of safety. This is also an optimized problem, and that is what I presented him for the turn project. One more thing is retaining wall. What is the retaining wall? If we'll go for also the basic Rankin's theory, there we are varying the theta value and finding out that particular theta value where the maximum is P active, minimum is P passive pressure. That we find out. So we have got optimization problem in geotechnical engineering. And yesterday also, those who have attended Alejandro lecture, there he was also saying that future is we can apply it as an optimization technique, this Bioinspired analysis. That's why I thought I'll just discuss on it. Again, now coming to foundation system. If I am going for a foundation system, I have to simply, I will also show it some example. If I go for a isolated footing also, first I have to see the geotechnical design parameters are satisfied, in that is bearing capacity, settlement criteria. I have to see also the structural design, what is RCC design or masonry structure, that design to be considered. And finally, economy is integral part of design. We have to see that the structure what you are building is optimum. Many times we ignore it. So this is what you see. Slope stability, we drew all these things. And we try, I am saying that we have got a popular software also, but this optimization tool are very preliminary. I mean, it's a very primitive hands. Nobody is using, they're using very sophisticated analysis method, but when going for searching, they are using very traditional optimization tools. What is the problem with these traditional optimization tools? These are different names in the optimization tools available. You can go to MATLAB. Now, when Leong was talking about, you were asking about that MATLAB, you go to the MATLAB, you just write down these things for a particular function. It will show you how to go, how to start and reach at the optimum points. But the problem, look at the curve here. If you will here, the optimum one, if you are close to this place, you will reach here. If you are close to this place, you are here. And if you are close to this place, you are here. But there is a particular, this is the true optimum in this total domain. So these algorithms cannot find it out. That is the most difficult part of this traditional optimization technique, which, as I said, in the slope stability or many textbooks available. So now, why this evolutionary optimization or bio-inspired analysis we need it? As I said, most these algorithms are initial point dependent. This happened due to multimodal. This is called as multimodal. Here is one optimum, here is one optimum, but this is the global optimum. So then algorithms are deterministic. If you go to the text optimization textbook, you'll see it is written. Do this, follow the next step, and so on. These steps are so rigid, you cannot go beyond it. Because nature, you see, though it follows certain rule, but it also changes with time, with situation. That part is missing in these traditional optimization tools. Another thing, discrete variable. Suppose I am going for a foundation design, I go for 2.391. The design, I mean, engineers say either say 2.4 or 2.5. So for that, what we need to go for? We need to search for an optimization tool. We can handle this. What type of foundation material I am using, concrete or steel? That is either 0 is suppose a concrete, 1 is steel. But these traditional optimization cannot take at a time, both. So all these problems are there, traditional optimization, for which we go for this bio-inspired optimization tools. But is it just new? Because as I'll tell you, this bio-inspired data analysis of recent origin of 30, 40 years. But is it the new now? No. If you look at this Fibonacci number, which most of you have heard about, 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and 55. So in the nature, the rabbits per generation follow this number, and this Fibonacci number has been inspired from this. You see this how it is. And we have this nature was following this rule. Now Leonardo da Vinci, nobody is sure. He might have been inspired and draw this famous art, which is supposed to be till date we call it the most beautiful. And some people feel the proportioning is beautiful, and that proportioning follow this Fibonacci number, which is bio-inspired, inspired from nature. So this genetic algorithm is basically based on Darwin's principle. Survival of the fittest. Fittest does not mean the strongest. Then dinosaur would have been still existing in our earth. So that is what that survives are the most, not the strongest, not the intelligent, but the one that is most adaptable to change. And there is an interesting animal on earth called tardigrades. It you see, it is virtually impossible to kill a tardigrade. You can freeze it, boil it, cross it, jab it in radiation and deprive it of food and water for years, and it will wiggle back to life. That is what called survival of the fittest. That means it can adaptable to change. This is another example how this grows. Suppose you see this giraffe. So he those who could reach survival for the next generation and they will have offsprings. Also in Darwin has said that it's not that that particular species will survive. It will also able to reproduce for the next generation offspring. That is called survival. So all these things has been inspired to think about genetic algorithm. Way back in 70s, John Holland, basically he is Professor of Electrical Engineering, University of Michigan. He tried to follow this adaptive process of natural system and to design this artificial system software which will have this robustness of the nature. Then when 75 he was trying to forget and he stopped everything. In 80s, David Goldberg, one civil engineer, he was working in a pipeline. He was searching for an optimization tool which can give him efficient system. As you know, there is a big competition. The company who can do at the minimum, he can only get the tender or to execute. So he found the traditional optimization is not good. So he went to Professor John Holland and asked him to tell this about genetic algorithm. He said, I think it will not work, but this David Goldberg worked on it and published a book, Genetic Algorithm. Then it became history. Now you'll go to so many, anywhere if you go for, you'll get so many things, genetic algorithm. And I was fortunate, his student, Professor Kalyan Mahdev, was teaching this course to us. So this, as I said, I had no idea about this biology, but there were some terms. When we derive something, we should give credit to the original one. So they were saying gene or genotype. So we are talking about phenotype, this actual physical characteristic. They were saying gene, I was saying my phi value or cohesion value. So then they were saying chromosome, then I was saying a particular value of C or phi. They were saying population. I was trying with, because in the slope stability, I was saying, there are so many parameters, there is geometry, XY. So that is what we call population. At a time, I was starting with different points. That is what they were saying population. I was saying my trial points. Then they were saying offsprings, the children. And we are saying that this first trial didn't fail. I tried with 100. Then I go for the next, another 100. So that is what we call offspring, children. Now I have shown you a diagram here. If you look at it, this is in the nature. This is my current population. One species, something different from others. And that's why I see now everybody is bothering about extinct creatures, animals. Because that is the beauty of nature. If the different species of different varieties are there, then someday a new species, more strong, adaptive, and sustainable, and everything, whatever we're talking about, may come out of it. So that is called current population. Then out of this, we find out who are the strongest out of these four. So suppose we found this is a fitness, here is 8 and here is 7. So these two survive and these two will die out. And then these two will have a crossover to have 2 more offsprings. But this during crossover, you see, even the siblings are not similar to look at. Because there is small changes. Even the twins also have some difference. How that difference comes? That difference is due to mutation. A small change. So they will not be, so there will be small changes in them, in the offsprings. Finally, I may get the 2 parents and 2 offsprings. Then original there were 4, now again 4, but there is a variability. So this variability in genetic algorithm mathematical form, we call it as initialized population, generation, evaluation, or that fitness assignment. Then we'll go for selection, crossover, and mutation. We'll go for the next generation and do it. So this is the inspiration from the nature, and we try to write down in one flowchart as an algorithm in computer science, because it started there. So they say call it as a genetic algorithm. So when I talk about this parent selection, I was saying out of these 4, I took only 2 which has got the best fitness. Nature has selected it, but when mathematics we want to go for, there are different ways. Like here I am talking about the tournament selection, there is a fight. So here it is very easy. Mathematically, I compare 2 values, which has the best fitness, I go for it. Another is a ranking selection, or I'll say the rank them and go with which has got the best, fitness. Then one more is called roulette wheel selection. You have seen that casino table. So there, whichever has the highest tower is a very small area. So what we do when I rotate it, there is a very least chance that it will reach here. But which has got small, you see, if some value is very high, so as you rotate, most of the time it may come. So if I'll go for next generation, so this will come many a times. So this is the technique we follow, that is a probabilistic rule. It comes, it is not deterministic. Because still, whichever is a very small area here, sometimes it may come. It's not that it will never come. But in deterministic, it may never come. So these are the different techniques we follow in mathematics, or this optimization tools to go for it. Here I have taken one example. So we generally do it in coding system, binary system 1001. But nowadays also you can go with real system. Initially started with binary coded. Then I can take it decoded value 2 to the power n. Then I consider, because I put the range x1 0 to 8, So accordingly, I can get x1 and x2 value. Then suppose I have got a function, I can get its function value. Then generally, I put this fitness, because if I am going for minimum, so then this I have to go for that, because genetic algorithm based on genetics, survival of the fittest. So if I am going for maximization, so the maximum value I have to go for. But if I am going for minimization, this should have the least fitness, so it should not be there. So look at this one. If I am going for here minimization problem, maximum function is there, it should not come. So minimum function, you see, maximum function has a fitness of 0.001, but minimum function has got a fitness of 0.049. That is the maximum fitness. So obviously minimum value will be chosen out of different alternatives. So this is how we do in a computer using genetic algorithm. And then in crossover, that time I was showing with some natural system of crossover, but here how you do it? So look at two colors here. So this is blue color, this is somewhat yellow color. If I swap it, so this, there are two, these are called as parents, father and mother, suppose a parent 1, parent 2. So if I make it crossover, so there is a swipe. In this, so this part goes up and this part comes down. So this is a different offspring. Two different offsprings, and though they are different of that mother or parents. Similarly, at 2 points I can swap it, or at different point I can swap it. So accordingly, it will be crossover. Finally, as I'll go this way, initially I might have started with points all around, but now all this will try to converge towards that zone where it is the maximum fitness value. So this process, it has evolved over the years. Now you see our human life, how it has evolved. Now we are none of our getting that previous generation what we had. One more issue is with this, our common optimization problem. So we call it as a multi-objective optimization. In this multi-objective optimization, we call it as a trade-off. Now everybody, when I'm talking about trade-off, all of you know, those who are already married or also in that, we have to now balance between the family and the work or profession. Everybody is under pressure to do it. So where to give the credit to what? Family or the work? It's not there in our life. It is everywhere now. Like world is passing through this very crucial period of sustainability. So sustainability is a trade-off between economy, environment, and social. So we have to make a trade-off. As you know, if I go for environment, I know how much it costs and other things. So this trade-off has given rise to any company you are working to think about this multi-objective optimization. What this multi-objective? They are all conflicting. Not that there are a number of objectives are more, but rather is conflicting objective. As I said, if you want to make it environmental good, but the cost is economy part is very difficult to manage. So in that traditional optimization, what we are doing, we are finding out some solution and going to ask our executive, whom you to give more weightage, environment, economy, or society. Then they'll give a point and then they'll come and they'll say, okay, this is one point. Next time, somebody will say, no, now give the weightage more to the society. So then it will change. More to the weightage, the economy, it will change. So how many times you will do this business? But that if I'll do it in a most like advanced evolutionary algorithm system, here I am talking about based on the genetic algorithm. So at a time, you will go with this solution to your executive. And he will say, so ask him, and he will say, what you want. So if he says, I want, this is the weightage, then you can choose. He will choose one. You don't have to come back again to your desk and do it and show it to him. So this is called as like here I was saying, look at this diagram. I have got two types of solution. Here is also a solution. Here is also a solution. But these solutions are called dominated solution or suboptimal solution. This is not good. This cost is more, but I am not, with the same cost, I could have get higher value, which is possible only if I am along this line. So basically in multi-objective, we try to find out this line. And to be more elaborate, look at this curve here. I am talking about environment protection and economic output. If you will higher economic output, so environment protection, and slowly you will see it is going down with this way. So what you want? You want at Q or at R or at S? Accordingly, you can say where will be the implication. And this front is called Pareto front. And this is not possible to use it within traditional optimization algorithm. So this is possible through a term called elitism. So this elitism is like, in the previous case, I was doing all this business of crossover, mutation, and so on. But there it was changing to the parents. But sometimes these parents may be very strong. It is better to take them directly. That is called as elitism. They will not have any this crossover. They will not have any fighting, nothing. So we always protect our king because they are the elite group. Some soldiers may die, but again may come out something else, but this has to protect. So they always are protected. This elitism, elitist groups are always protected. So based on that, I'll go now some examples. Simple examples of this foundation design. Look at this. We'd go for L, B, depth, because here we take only bearing capacity and suppose a bearing capacity, factor of safety and settlement. But also I need what is the concrete, what is the reinforcement, what is the depth of foundation, soldering. If I'll go for everything, that is what I have done with ARCIS foundation as per American Concrete Institute code. So then you will see, if I take single objective, so this is the cost and this is the dimension. But if I will consider it, and I will say the settlement, I cannot go for 25, I want to go for some reduce. Then at a time, I can give you all the solution, go to the executive and ask him what you want. Settlement, this is okay? Or you will say, no, I want less settlement. You take this less settlement. Factor of safety is okay with me. Or if it is factor of safety, you can reduce, go there and take this is the cost. You see, this cost, if I can reduce the factor of safety, it can go up to 517 USD. But if I want to go for factor safety 3 here, but settlement less, it go to 830. So every alternative, at a time you get it and go to your executive, show it, he will be happy to choose anyone. Like another one here, I have shown with a slope stability method. So you will see I have shown with simply a waste containment system, and this is the history of failures, and this is a quantity of waste involved in failure. So at a time, if I'll go for this objective, multi-objective, I can find out the way it may fail, what is the factor of safety, and also I can calculate how much volume of waste will be generated through that. So now you have got the most, for your executive, it will be a very good decision. Very good, I'll say choice to take the decision accordingly, take preventive measures or mitigation measures. Here I have shown with another example, geosynthetic reinforced earth wall. So here I have taken some very small and typical examples so that all basic idea about geotechnical engineering will be able to understand it. So these geosynthetic retaining walls or reinforced earth walls are very common. So I gave that at a particular point, the cost, and then I want to also minimize the tensile strength of that geostrip because that is the main cost. I also want to reduce the length of the geogrid. That involves a cost. And for a particular height, taking all these things, what will be the total cost? So at a time, I'll get a set of solution. For a particular height, I can get the cost, length of the geogrid, and corresponding tensile strength of it. So here, I am not this, based on this analytical method available, the limiticular methods available, I am only putting in a form of optimization analysis and giving with alternatives. Optimization tools is very good for taking the level, higher level decision. So another thing, interesting, I found nowadays many GRE wall, they are putting these different types of fill material. And one of them is thermal power plant fly ash, where I found this phi value varies from around 28 degree up to 41 degree. So how this fill also going to change? That also you can put it with the different heights of embankment, with the phi value varying from 30 to 45, how they will change. So this analysis I can do using this again, multi-objective genetic algorithm. So this is again variation with seismic coefficient. If the seismic coefficient is varying from 0 to 0.2 to 0.4, because here that time previously there was no seismic, but this is all pseudostatic analysis, keep in mind. And even variation with the unit weight of that fill, because as I said, fly ash is a lightweight material compared to the natural sand. So they accordingly this unit weight also may vary, and that also you can make a variation. At one go, you can get so many solutions and you can give alternative to for the higher level decision making. And one more example. This is sometimes, many times there is not a very specific formula. People say how to go for bearing capacity of the topmost earth bed. Then either I'll go for a single layer, 2 layer, or 3 layer. If single layer, what should be at what depth, what spacing, what should be the width? So there is one, I'll say that one analytical solution by Mikulowski. That is what I have followed and try to find out what the common people use. It called bearing capacity ratio. This cost right now, don't look at this value because I had taken a theoretical value which was available in 2007. So that value might have changed many folds. So that you don't look at, and in your country may also it may be different. So as you put single layer, so maximum we can go up to this one or 2. It is also becoming difficult, but because of a particular layout. Because I am going for double layer or triple layer, but you see here, if you want to achieve more BCR than a particular value for a particular arrangement, then the cost sharply increases. So there you have to say there is no point in increasing. If you want to increase, so this is not a good solution. You have to change some other parameter. So these type of information you can do it. And again also you see, as I was saying, geogrid strength is very important. So for different strength of this all theoretical you have to consider. So there is an optimum value beyond which if you want to increase the BCR value, it sharply increases cost. Sorry. So here I have tried to give one more example. I have 5 minutes more. So very interesting some analysis we do, but the like particular rock failure criteria, the material may not have uniform strength, and if I fit a particular failure criteria to it, many times we don't get a proper fitting to the curve. Why it is so? That's why I try to follow sorry, some other method here, we call it as a identify the outlets. You see, this layer only was trying to change. Just a minute. Sorry. So that is called as least median square. And that using that you can remove out this outlet. Hello? Am I audible?
Yes, Professor, you are audible. Please continue.
Okay. So once I remove those things, so you will see these outlets, they will see I am getting a better fit with mean square error reduced from 70.61 to 14.51. This is only possible with evolutionary algorithms. I tried with all traditional algorithms, it failed. And this is the method is called reweighted Lisper method, where you can remove the outlets through least median square method. Because by default, we follow least square method. Another issue, I have shown with only one example, you can put also in your problem. When you fit a curve, here I am talking about fitting an experimental curve of sigma 1, sigma 2, sigma 3, three-dimensional triaxial, rock triaxial test. What do we assume? We assume as if sigma 2, sigma 3 is, they are very perfect value. And also, because in fact, what we assume, my independent variables, x1, x2, x3 is very perfect. Only y make the changes to find out what is the parameter through minimizing the error between the predicted and observed. But when I'm doing everything in one instrument, there could be error in both sigma 1, sigma 2, sigma 3. Or if I am measuring some parameters, so if there is an error in y, there should be also error in x1 and x2 and all these independent parameters. So that type of statistical analysis called as error in variable. So it is not very common in geotechnical engineering, but sometimes it will require, because when I am going for really sophisticated analysis to fit a proper data. So that is called as reconcile data, because then I have to identify what is the error in my machine, 0.01, 0.001. This error is in sigma 2, sigma 3, so also sigma 1. Then I can get the reconciled value. So that reconciled value to fit the model simultaneously is called error in variables. That is what I have done it here. And that is only possible using this evolutionary algorithm. Not traditional optimization algorithm cannot solve this type of problem, because the number of variables here goes on 100, because depending upon the number of data points. This is another one based on this also. Geotechnical engineering analysis, one more thing we do some prediction models. Like, think about, I'll go to that first later, say, liquefaction analysis. In this liquefaction analysis, which those who are geotechnical engineering, for them, it is not a problem, but for others, somebody in microbiology and others, I'll say that here the soil behaves like a liquid when it is vibrated during earthquake. So here there is no mechanistic model. What we do, we go for statistical method based on this data. We go with some data at the site or in the laboratory. Then we check in the history, has it liquefied? Then we say, based on that, we fit a model. And this we are following since 1971 seed and itris model. But as I was saying, optimization, that genetic algorithm, if I do for statistical analysis, we call it as a genetic programming. So that same crossover mechanism, look at here, that parents that I was saying 1001 and so on. But here, one expression I am taking it. Tan x1, x2. Tan x1, x2. x1 into x2, tan. And the another parent is, you see, log x3 of yours is sin x2 plus x1. So then I'll swipe. What I'll do, there I was taking only one. Here I'll swap this one, total 3. That's x1 into x2. x1 and x2 will come here, and this sin x2 plus x1 will come this side. So this way I'll get different types of offspring. And this is what a typical tree, it is called tree-based, and that is called genetic programming. And you see what I have done. Here I mentioned tan 6.5 x2 minus x1. So in this also I can write down in node. In computer, they very much understand this node. So that's, they have developed in this fashion, and we can now use it. So then also here we can do mutation. What is this mutation? A small change. So it was a tan x1 by x2. I can make it tan x1 into x2. So you see tan x1 by x2. If I mutate it, means division change to multiplication. Becomes tan x1 into x2. This is called mutation in mathematics. And then if I put it 2 genes, I can write down it as one expression. This is called multi-gene genetic programming. And using this multi-gene genetic programming, I'll show you some results what our students have done it. So basically we want to find out the limited function, that expression which will differentiate liquefied and non-liquefied state. This is what statistical method, the success rate is 89 for liquefied case and 78 for non-liquefied case. Total is 84. Whereas if I'll compare it to our present method, MGGP method, so it is equally efficient for liquefied and non-liquefied case of 87 and 88%, overall 87%. And as you know, another Bioinspired is there that today I didn't want to discuss it. That is called artificial neuron-based method. So there also, this is imbalance 82 and 90, but overall is close to that, this model equation based, that is MGG based liquefaction, that is 86%. So 86%, 87% compared to statistical method is better, and particular non-liquefied cases, this is better. And similarly also you can do is for probabilistic model with, and it's compared with Juan's method, Olson's method, this probabilistic based liquefaction analysis, then also Robertson's method, and this one with MGG method. And in overall see, this genetic algorithm based, that is multi-gene genetic programming, has performed better than the presently available statistical method. So now I have come to, because this is just, I have tried to say what are the capabilities of this Bioinspired analysis in geotechnical engineering to very simple problem. Right now, we are also applying to many advanced methods. Like now people are also using other evolutionary method called ant colony optimization method, firefly optimization method, particle swarm optimization method, and so on. These are all derived from nature. Looking at that, how these ants, they transport the goods you might have seen in during our childhood. So that has become a tool. The tool will help to formulate in mathematics going for or solving these difficult problems. This can supplement the physical mechanist model, particularly for project optimization and higher level decision making. This is also a very good tool for in probabilistic method. And as a geotechnical engineer, we should closely follow this developments in artificial intelligence and evolution optimization methods. Mostly it develops fast in electrical or computer science. So we try to follow it. That is what I have learned from them also. And right now, as in the other talks, we are learning from microbiology, this biogeotechnics. Thank you all. They are all my students. Now I'm happy to take any question from the audience. So there is no panacea. These numerical methods, they are not exact methods, analytical methods. All they have got pros and cons. So then many times we just look at if somebody has done similar problem and he has failed. So whichever is better, we follow that. Otherwise, for a new problem, we try with different alternatives to find out the best model. Okay, so when we have got sparse data, as I said you, then other techniques in addition to genetic algorithm, it becomes particularly important to go for better with less number of data. So in that case, sometimes we generate artificial data based on the existing data and extend the database to fit a model. That is the best way to do rather than searching for, going with less number of data. Because like in the liquefaction model also, we try to develop some artificial data points based on a probabilistic rule so that the developed model will have better adaptability or what I'll say that better dependability or robustness. So for in that case, we have to go for development of the more artificial or I'll say, more database based on this probabilistic method. That is very important in the the question, but what I say, just I take one example from say, I don't know, or suppose say, I'll say when we want to learn driving, so that's better. So initially, one driver is to sit close to you to tell you all these things, and it becomes very easy to drive. Then after few days, you get a license, just a learner's license. So that time, because when you are learning, that vehicle is different. There are two controls, one is with you, another control is with the driver. So that is what we call as a training. But when it comes to testing, so that time, there is only one control with you and then you go driving. But still there is somebody looking at it or observing, so they can identify your flaw. But when it comes to finally the validation, you are all perfect and you just try with a new track, and if you pass there, then it becomes a perfect driver. That is the basic difference between the training or the learning and testing, and then finally the validation. In cricket also we follow that. Like somebody plays the county cricket, then go for test match one day, then go for a different pitch. So everywhere he feels that comfortable, then only you can say he's the best batsman.